Since particles are often charged in solution, we might guess that if we have particles that are the same, then since they have the same charge on the surface, that they would repel each other. And that can happen. So imagine we looked at a little graph of surface potential, or potential rather, and we looked at two different particles. So we've got a particle here, and we'll just look at a little slice of that particle, and another particle here. So we can imagine this maybe being a spherical particle here. Great. And in between we have a solution with some electrolyte in it. Now what's going to happen to the potential, if we looked at the potential in this space, what we'd find is that, let's just graph it like this. So we've got potential, and we have a space here, is that at the surface it's quite high here, and it dies off. And let's imagine that the Debye length is much shorter than the distance between the particles. So perhaps we have a Debye length of maybe a nanometer or so, and the distance between the particles might be 100 nanometers. So since the potential dies off to zero, that means is that in this area here, there's no overlap between the potentials, and so this would be almost no repulsion, because they just don't feel the electric field from the other particle. On the other hand, if we move those particles closer together, or indeed if we didn't move them closer together, but we just had very little salt in this space, in the solution, maybe the ionic strength is very close to zero, so the Debye length is very long. Then if we were to graph potential as a function of distance, what we'd see is that it dies off very slowly, and at the place between the particles, it doesn't die off to zero. So this particle is able to feel the electric field from this particle and vice versa. And so in this case, we have repulsion. And so we can actually work this out mathematically. The equations to use will differ whether you're using plate-like particles or spheres. I'll show you the examples for spheres next. All right, imagine we have two particles that of radius r, and they're separated by a face-to-face distance of h. The potential energy for the interaction, the electrostatic interaction between those particles, is given by the following equation. In this equation, we've got 64 times pi times the radius of the particles. This is the number density, the number per meter cubed for the concentration of the electrolyte. We've got the thermal energy kT. Cap gamma naught is this hyperbolic tangent. It's really a measure of the balance between the electrostatic energy on top here and the random thermal energy on the bottom, telling you whether there's, basically if the top is much bigger than the bottom, we call it a high potential case. It means there's a lot more electrostatic energy than there is random thermal energy. Kappa, the reciprocal of the Debye length, is both in this exponential and at the bottom of the equation. I should point out that this equation is for a symmetrical electrolyte, so that is one that is either 1 to 1 or 2 to 2, like that, where the charges in the anion and the cation are the same. Okay, well, this is a bit of a beast, and so it would be nice if we could simplify it. So we can do that if we remember the properties of the hyperbolic tangent. So if x is small, we'll say much, much less than 1, then the hyperbolic tangent of x is approximately equal to x. In this case, that would mean that the fraction here is much less than 1, which would mean the potential is small relative to the thermal energy. We'll call this the low potential case. Conversely, if x is much greater than 1, the hyperbolic tangent of x is approximately equal to 1. So we call this the high potential case. So we're going to plug both of these approximations in for the high and low potential case, and that way we get a much simpler expression for the energy of repulsion between two charged spheres. So in the low potential case, we're plugging in that the result of this hyperbolic tangent is just the argument, right? That the hyperbolic tangent of x is approximately equal to x. So we'll plug that in. So we have 64 Okay, so you write that expression again, 64 pi r c naught kt. So that's all written out the same. And then we replace our gamma naught squared with this expression. So we're just plugging in the approximation for the low potential case. And we also have to plug in this exponential, which I've forgotten to write, e to the minus kappa h. And then on the bottom, what we've got here is the kappa squared. I've just written in explicitly the expression for kappa squared, remembering that since it's a symmetrical electrolyte, in other words, something that's a positive 1 and a negative 1, or a positive 2 and a negative 2, we can just put a 2 in there for that sum of all the ions, right? So we just write it for the cation and then write it again for the anion, so that's why it's times 2. Okay, so by writing it out explicitly like this, we can see there's lots of places where we can cancel charges and kts, and when you're done crossing everything out, you get a relatively simple expression. So for the low potential case, we just get 2 pi r, the potential squared, the dielectrics, and then an exponential decay with distance h. So this is the expression for the low potential case for repulsion between spheres with charged surfaces. When you do your unit analysis here, you'll see the units come out to be joules, because this is the amount of energy for a single pair of charged particles. We just noticed that this hyperbolic tangent we said was going to be approximately equal to 1, so we just set that to 1, and we have our result. And going through this, we have 64 pi times the radius of the particles times the number concentration of the salt, the thermal energy kT, minus kappa, the inverse Debye length, h, the distance between the face-to-face distance between the particles, and kappa squared. Okay, so this one will also give units of joule since it's per pair of particles, colloidal particles. You should notice that there's no expression in here for the surface potential, and that's because we already factored that in by saying this was the high potential case. So this is at the limit of high surface potential, this is what you get.